You're sitting inside an M1 Abrams, 70 tons of steel, the most advanced American battle tank ever made. You're tearing across rough terrain, hitting speeds of 70 kilometers per hour. That's over 40 miles per hour. The tank absorbs the bumps, smoothing them out. No bone-jarring jolts. The crew can aim and fire even while moving. The stabilizer works perfectly. Pure American engineering, you think. But every time that M1 Abrams rolls over an obstacle, it's relying on German suspension technology from 1942, invented by Professor Ernst Lehr for the Panther tank, stolen through Operation Paperclip. And today, the M1 Abrams, the Leopard 2, the T-90, the Challenger 2. And virtually every modern battle tank in the world uses that same system, torsion bar suspension. A German innovation from 1942, dominating modern tank construction 83 years later. Let me show you how a German professor invented a revolutionary suspension that the Americans couldn't develop and were forced to steal. 1941, the Soviet front. German Panzer III and FE tanks are battling Soviet T-34s. German tank commanders are reporting a problem. The T-34 is faster across rough terrain. It can cruise at 50 kilometers per hour across fields, where the German tanks can only manage 30. Why? Suspension. The T-34 uses Christie suspension. Large vertical coil springs, allowing for long travel. The tank can navigate obstacles without shaking the crew to pieces. German Panzer III and IFU tanks use leaf spring suspension, old technology. Like a truck, it works on roads, but it performs poorly off-road. Short travel, harsh impacts. The crew gets bounced around. Accurate aiming while moving is impossible. The T-34 can drive and shoot. The German tank has to stop to aim. The German military's generals are worried. They need a new tank. Faster than the T-34, better armored, better gun, but above all, better suspension. The contract goes to Daimler-Benz and MAN to develop a medium tank, codename VK30.02, later known as the Panther. 1942. MAN engineers have a problem. The new tank is supposed to weigh 45 tons, much heavier than the T-34's 26 tons. Christie suspension won't work for 45 tons. Too weak. The coil springs would break. Leaf springs like the Panzer IV, also not good. Too harsh. Too little travel. What's the alternative? Professor Ernst Lehr is consulted. He's an expert in vehicle suspensions. Working at MAN since the 1930s, he has a patent for torsion bar suspension. But torsion bars have a problem with heavy tanks. Let me explain how torsion bars work. A torsion bar is a long piece of metal. One end is fixed to the tank chassis. The other end is connected to a swing arm. The swing arm carries a road wheel. When the road wheel hits an obstacle, the swing arm twists. That twists the torsion bar. The metal wants to return to its original shape, creating spring force. Very simple, very robust, no complicated mechanisms. But the problem is, for a heavy tank, you need a strong torsion bar. A strong torsion bar means thicker or longer. The Panther is 3.4 meters wide. That's about 11 feet. The torsion bar can't be longer than the tank's width, otherwise it won't fit inside. At 3.4 meters long, the torsion bar is too weak for 45 tons. Lehr has a genius idea. Instead of one long torsion bar per road wheel, use two shorter bars. One runs to the left, one runs to the right, both connected to the same swing arm. That doubles the spring force, without making the tank wider. The effective bar length is now 6.8 meters, that's over 22 feet. Double the tank's width, enough for 45 tons. Let me explain that more precisely. Normal torsion bar, swing arm in the middle of the tank. The torsion bar runs to one side. Length is limited by the tank's width. Lehr's double torsion bar, swing arm in the middle. 2 torsion bars, one runs to the left, one runs to the right. Both work together. Effective length doubled. Spring force doubled. Geniusly simple, but no one had ever done it before. 1942. The first Panther prototypes with Lehr's double torsion bar suspension are tested. The results are exceptional. The Panther weighs 45 tons. It travels at 55 kilometers per hour off-road. That's almost 35 miles per hour. Faster than the T-34, despite 20 tons more weight. The suspension travel is 25 centimeters. That's almost 10 inches. Much longer than the Panzer's 10 centimeters. The crew can aim while moving at full speed. Stabilization works. The T-34's advantage in mobility is eliminated. But Lehr's system has another advantage. Maintenance. Torsion bars are robust. No moving parts except the swing arm, no coil springs that can break, no leaf springs that fatigue. A torsion bar can last 10,000 kilometers, over 6,000 miles, before it needs replacing. Panzer IV leaf springs last only 3,000 kilometers. T-34. Christie springs last 5,000 kilometers. 3 times the durability means less maintenance, fewer spare parts. The tank remains operational. Longer. The German military is thrilled. Orders mass production. 1943. The Panther goes into production. First deployments at Kursk, July 1943. Technically, the Panther is superior, but reliability problems. The engine overheats. The transmission breaks. Not because of the suspension. The suspension works perfectly. The problems are the engine and drivetrain. These are fixed later. 1944. The Panther is refined, becomes the best German tank of the war. Many military historians say the best tank of World War II, period. The 88mm gun kills any Allied tank at 2,000 meters. That's over a mile. Front armor 80mm sloped. Can't be penetrated by a Sherman. Mobility thanks to Lehr's suspension. Surpasses all Allied tanks except the M18 Hellcat. Allied tanks have inferior suspension. The Sherman uses vertical coil springs, VVSS suspension, vertical volute spring suspension. It works, but travel is short, 18 centimeters, about 7 inches. The Sherman rides hard. The crew gets shaken up during off-road travel. The British Churchill also uses coil springs. Even worse, travel only 12 centimeters, under 5 inches. The Churchill is slow and uncomfortable. The Soviet T-34 uses Christie suspension, better than the Sherman. Travel 30 centimeters, almost 12 inches. But the Christie system is complicated. Large coil springs inside the tank. Take up space. Reduce ammunition storage. Springs break frequently. Replacement is difficult. Requires removing the entire spring unit. Only one Allied tank has torsion bars. The British Cromwell uses simple torsion bars. Not the double system. Travel 20 centimeters, almost 8 inches. Better than the Sherman, but not as good as the Panther. The Cromwell torsion bars are shorter, weaker. The Cromwell weighs only 28 tons. For a heavier tank, they wouldn't work. 1944 to 1945, the Allies capture German tanks. They examine them, analyze the suspension. British and American engineers are impressed by the double torsion bar system. They write technical reports. Recommend, copy this system for future tanks. But the war is almost over. No time to develop new tanks. The Sherman has to do. The Tiger I and Tiger II also use torsion bars, but not Lehr's double system. The Tiger uses single thick torsion bars. Each bar as thick as an arm, very robust, but heavy. The Tiger tank weighed 54 tons, partly due to its massive suspension system. Professor Ernst Lehr's double torsion bar system was more efficient, lighter. providing the same spring force with less weight. May 1945, Germany surrendered. Operation Paperclip began. American teams were searching for German scientists, engineers, technical documents, weapon systems. One of their targets, tank technology, specifically suspension systems. The American army had a problem. The Sherman tank was adequate against Germany, but the Sherman couldn't compete against the Soviet IS-2 or IS-3 tanks. The IS-3 had a 122mm cannon and 200mm of armor. The Sherman had a 75mm cannon and 50mm of armor. No chance. The USA needed a heavy tank. Fast. Development began on the M26 Pershing, a heavier tank, 41 tons, 90mm cannon. The problem? What suspension system to use? The Sherman's VVSS suspension wouldn't work for 41 tons. It was too weak. Coil springs would break. What was the alternative? Engineers studied captured German tanks. They had access to Panther wrecks. They examined the double torsion bar system. They understood the principle. Professor Lehr had made it genius. 2 bars per road wheel, doubling the effective length. It could carry a heavy load. It was robust and easy to maintain. The decision was made. The M26 Pershing would get a torsion bar suspension. Not exactly Professor Lehr's double system. The Americans simplified it. They used single long torsion bars, but the principle was the same. It was the first American mass-produced tank with torsion bars, directly inspired by the German Panther. The M26 Pershing arrived too late for World War II. Only a few saw combat, but they became standard tanks from 1946 to 1948. In the Korean War in 1950, the M26 fought against North Korean T-34-85 tanks. The torsion bar suspension worked well. Better than the Sherman's VVSS, but the M26 was underpowered, slow, and it was replaced by the M46 Patton. The M46 Patton, the M47 Patton, the M48 Patton, the M60 Patton. They all used torsion bar suspension. Each generation improved the system, but the basis remained the same, the German principle from 1942. For over 30 years, American tank development was based on Professor Lehr's invention. The Soviet Union did the same thing. The T-34 tank had Christie suspension. It was complicated and maintenance-intensive. Stalin ordered, "Develop a better tank." The T-44 tank was developed in 1944. It used torsion bar suspension. Where did they get the idea? From captured German Panthers. The Soviets captured hundreds of Panthers on the Eastern Front from 1943 to 1945. They examined them. They copied the suspension. The T-44 used torsion bars similar to the Panther, not exactly the same. The Soviets made their own adjustments, but the principle was German. The T-54 followed in 1947. The most famous Soviet tank, over 80,000 were built. It used torsion bar suspension. The T-55, the T-62, the T-64, the T-72, the T-80, the T-90. Every Soviet and Russian tank since 1944 has used torsion bars. They all go back to Professor Lehr's Panther design. And then in the 1970s, the USA developed a new tank. The MBT-70 project failed. It was too expensive. Too complicated? It was restarted as the XM-1 project, which became the M1 Abrams, the most modern American tank. It was introduced in 1980. Guess what suspension it used? Torsion bars, 7 road wheels per side, each mounted on a torsion bar. The M1 Abrams torsion bars aren't identical to the Panthers. Technology has evolved. Metallurgy is better. Dampers are more modern. But the fundamental principle is the same. A long piece of metal twists, creating spring force. Exactly like Professor Lehr designed in 1942, Germany also developed a new tank. the Leopard 1 in the 1960s, the Leopard 2 in the 1970s. Guess what suspension they used? Torsion bars with hydraulic dampers. The Germans are still using their own invention from 1942, but now they have to pay for it, because Professor Lehr's patent has expired. The technology is public domain. Everyone can use it. Great Britain developed the Challenger 1 and 2. Torsion bar suspension. France developed the AMX-30 and Leclerc. Torsion bar suspension. Israel developed the Merkava. Torsion bar suspension. China developed the Type 99. Torsion bar suspension. Japan developed the Type 90 and Type 10. Torsion bar suspension. Practically every modern main battle tank worldwide uses torsion bars. The only exceptions, the British Chieftain used Horstman suspension with coil springs. It was inferior and was replaced by torsion bars on the Challenger. The South African Oliphant also used coil springs. It was modernized with torsion bars. It's estimated that over 100,000 tanks worldwide have torsion bar suspension. They are all based on the German design from 1942. Professor Ernst Lehr invented it. The German military used it. The Allies stole it. And now it dominates global tank design. But here's what almost no one knows. Professor Lehr developed the double torsion bar system, not just for the Panther. He patented it in 1938, 4 years before the Panther. The original patent was for half-track vehicles. The ZKFZ 251, German armored personnel carriers. They used Professor Lehr's suspension starting in 1939, so Professor Lehr invented the system in 1938. The German military used it in half-tracks in 1939, adapted it for the Panther in 1942. The Allies discovered it from 1944 to 1945. They stole it. They used it starting in 1946. And today, 87 years after its invention, it's still the standard. Why is torsion bar suspension so dominant? Several reasons. Simplicity. No moving parts except the swing arm. Coil springs have coils that can break. Leaf springs have layers that can separate. A torsion bar is a solid piece of steel. It's very hard to break. Robustness. A torsion bar can carry an enormous load. The M1 Abrams weighs 70 tons. The torsion bars hold. The Leopard 2 weighs 62 tons. The torsion bars hold. The T90 weighs 46 tons. The torsion bars hold. No other suspension system can carry so much weight so reliably. Maintenance friendliness. Torsion bars last 20,000 to 50,000 kilometers before replacement is needed. When replacement is needed, it's simple. Loosen the swing arm. Pull out the old bar. Slide in the new bar. Remount the swing arm. 2 hours of work. Coil spring replacement takes 5 to 8 hours. It's more complicated, more parts, space efficiency. Torsion bars lie horizontally in the tank floor. They don't take up any vertical space. Coil springs need vertical space. They reduce interior space. The T-34 tank with Christie suspension had large springs in the fighting compartment. They hindered the crew. The Panther with torsion bars had more usable space. Cost. A torsion bar is cheaper to produce than complex coil spring systems. It's a single piece of steel, heat-treated for elasticity. That's it. No assembly of multiple components. Cost efficiency is important for mass production. The T-54 was built 80,000 times. Torsion bars allowed cheap production, but torsion bars also have disadvantages. Why doesn't every vehicle use them? The problem is weight. A tank is heavy enough that torsion bars work. A light vehicle needs thin torsion bars. Thin bars are less efficient. For cars or light trucks, coil springs are better. But for anything over 20 tons, torsion bars are superior. Another disadvantage, adjustment. Coil springs can be easily compressed or extended for different loads. The torsion bar, it has fixed characteristics. You can't simply adjust it. If you add heavier armor, you need a thicker torsion bar. Not just an adjustment, a replacement. But for a military vehicle with a defined weight, this isn't a problem. Now, a modern trend is hydropneumatic suspension. The Leclerc tank uses it. The K2 Black Panther uses it. It allows for active suspension. The tank can lean, improving the targeting angle. It's more expensive, more complicated, and requires more maintenance. But it offers advantages that torsion bars do not. Despite this, most modern tanks stick with torsion bars because of their reliability. Let me show you how completely Professor Ernst Lehr's dominance is. Here's a list of all modern main battle tanks. By country: USA, M1 Abrams, torsion bars; Germany, Leopard 2, torsion bars; Russia, T-90M, torsion bars; China, Type 99, torsion bars; UK, Challenger 2, torsion bars; France, Leclerc, hydropneumatic, but based on torsion bar principles; Israel, Merkava, torsion bars; Japan, Type 10, torsion bars; South Korea, K2, hydropneumatic; India, Arjun, torsion bars; Pakistan, Al-Khalid, torsion bars based on the Chinese Type 90. Of the top 10 tank-producing nations, 8 use torsion bars directly. 2 use advanced systems that are based on torsion bar evolution. 100% have German WW2 technology in their lineage. Everyone, without exception. That is complete dominance. Production numbers show the scale of this. M1 Abrams, 10,000 built. Leopard 2, 3,600 built. T-90, 1,000 built. T-72, 25,000 built. T-55, 80,000 built. Type 99, 600 built. Challenger 2, 400 built. Merkava, 2,000 built. Leclerc, 900 built. In total, over 120,000 modern tanks with torsion bar suspension based on Professor Lehr's design. And that doesn't even count the older tanks. M60 Patton, 15,000 built. M48 Patton, 12,000 built. T62, 20,000 built. T64, 13,000 built. Leopard 1, 6,000 built, all of them using torsion bars. Add another 60,000 tanks, making a grand total of 180,000 tanks over 70 years. Using Professor Lehr's invention, this isn't just technology transfer, it's complete dependence. The Western tank industry couldn't develop a better alternative. The Soviet tank industry couldn't either. Chinese, Israeli, Japanese engineers, they all tried. No better solution for heavy vehicle weight has been found. Professor Lehr's 1938 design remains optimal. Compare this to other German WW2 technologies. The V2 rocket influenced the space program, but was replaced by more modern designs. The Me-262 jet engine was a beginning, but jets evolved dramatically since then. But torsion bar suspension, almost unchanged. Materials improved, dampers were added, but the fundamental mechanical principle is identical to 1942. That shows true genius. Professor Ernst Lehr created a design so efficient, so optimal, that 87 years of development couldn't significantly improve it, only refine it. That is a sign of perfect.